And it will take 2 days to cover. It will be homework 9 and 10 from the book. And it will be a lesson on L'Hopital's rule, which does belong in this unit, which is an application of derivatives unit. That's the title of this unit, Unit 4, Applications of Derivatives. And those, thank you guys for your attention. Those applications have been diverse, from curve sketching to optimization, related rates, to Newton's method, all things, and mean value theorem and extreme value theorem at the beginning, all things that are things now we can do after the Unit 3, having studied A and B, studied every which way of taking derivatives of every function you can think of using the various methods. So this is the last of a set of applications we've been studying. And this takes us all the way back to Unit 1, or rather, I guess Unit 2 we called it. We're going to be evaluating some limits today. So this is like revisiting some of our, going back to our roots. In fact, the very first problem I'll give you today is one that comes from Unit 2. This is the historical footnote just to justify the name of the lesson here, L'Hopital's rule. It actually was developed, as many things in math, they get misnamed, by Bernoulli, one of the Bernoullis. And L'Hopital is maybe more famous for the fact that for his first text, one of his very famous calculus texts, where he uses this technique and people then just adopt this moniker for this rule and give it his name, even though it was really Bernoulli who taught L'Hopital about it. And there are some, there you go, some black and white dead European guy photos for you. Okay, there you go. Which hairstyle would you prefer? The high or the lower profile? Okay, go for the high. All right, so let's show you a limit. I'm just going to rush through this one because it's one you've done before. Let's show you a limit that we would have given you in Unit 2. But when you first encountered this in Unit 2, I just want to make sure you remember the cognitive dissonance you had. You were like, okay, well, I just plug in 2. Oh, wait, it's like you get 0 over 0. And that moment, you experienced something at the time that we didn't label an indeterminate form. But today we'd like to actually say that this is what we call an indeterminate form. One of actually many different indeterminate forms that we'll run into today and tomorrow. 0 over 0 is what we call an indeterminate form. And in Unit 2, we handled it just by doing this algebraic trick, if you'll remember, right? So we'll skate over the details. I just assume that that's a thing you remember doing, yes? It's like how we handled that situation. And if you were like a pre-calculus student, you might be saying like, oh, it's like a hole on the graph. Like that's what's happening geometrically. So this might be, it might be overkill to use L'Hopital's on this, but we'll use this as our first example of L'Hopital's rule in a minute as well. But let's first tell you what L'Hopital's rule is, say how it can maybe help us with indeterminate forms like the one we just looked at here, and give a short proof of L'Hopital's too, because it's not too hard. Hopefully we're saying that right, by the way. French people can correct me, but we got all these good French names. Oh yeah, it should be pronounced hospital. Hospital. Yeah, I think that's right.
Yeah, the L is silent actually. It's just hospital.
Yeah. Lopital. Maybe it's Lopital. No, it's L'Hopital. All right. So here's one, I should say, one statement of L'Hopital's rule. This is not a minor point, this first point. It says, suppose that f of a and g of a are both 0. Notice that if we have a function, a rational function like the one we were just doing, for the particular value a, which was 2 on the last one, for that value, f of 2 and g of 2 were both 0, right? So that, therefore, that's a situation in which L'Hopital's could be applied, apparently. So that's the hypothesis. And then, and they're differentiable, of course. And of course, provided that g prime isn't undefined. By the way, this is a comma, in case you're wondering. Is that okay?
Yes.
That's a comma. Everyone look, that's a comma. I just want to make sure everyone's okay with that. It's a comma. It's not, because it's grammatically correct. Then this, comma, if the latter, it's grammar. It's like, why, there's a comma there.
It wasn't 5 minutes.
Then I would
It
agree.
wasn't
No.
5 minutes.
That's a lifetime of learning, because next time you encounter this, you'll be like, oh, that's a comma.
No.
Yeah, you will. Yeah.
And also, how will I know when to pause in the middle of the sentence?
Why is there a comma and a period?
That's my curse. All right. So the result says that the limit we just took is, now careful. This is not the quotient rule. Just make sure you're clear. This is like, in some ways, kind of the poor man's quotient rule here. We're taking the derivative of the top and the derivative of the bottom. Now, why does that even work? It seems in some ways like it's like kind of breaking the rules or something like that. But let me just, let's actually prove it. Here's a quick proof that this actually works. Starting with the right-hand side, let's just justify that this limit, where we have derivatives on top and bottom, is the same as the limit that we started with. So notice what I'm doing on top and bottom. What am I replacing top and bottom with? F prime of x is equal to this. Oh yeah, that is the definition of the derivative at a, right?
Sure.
Or the definition of the derivative of a for g. Right. Difference quotient, right? y1 minus y2, okay, whatever. X minus a's can be canceled out. The limit as x goes to a can be collected using one of our limit properties. And now, how do I make this move right here? What justifies this next equality? Because why? Yeah, I told you that this is not just cosmetic, this is critical. This part of the hypothesis is now being used. It was a given, apparently. If you're going to use L'Hopital's, you've already guaranteed to me that f of a and g of a are both 0. So may I replace those with 0 and 0? Of course I can. And the result follows, okay? Now, intuitively, this should make sense too, because remember what we've been discussing recently, especially as it relates to the linearization of a function. Remember this? I said that, hey, think about sine x over x, for example. What really, again, the pre-calc student thinks that maybe there's a vertical asymptote at 0, because like, the denominator is undefined or something, right? But you know better. You know that both of these act like this diagonal line near there. And so you and I both know that really, you know what vertical asymptotes are about? They're really about rates of change. And doesn't that kind of capture what we're talking about here? We're saying that it literally, it's not just kind of like rates of change, it really is. It's exactly what it's like. So let's return to the example we were just looking at, the one.
Are you writing down the whole proof?
I am.
Thank you, John. I appreciate your passion for the subject. Let me give everyone a second to write
Wait,
that.
Johnny, did you get the comma?
I
did. It's right here. It's right here. I'm a linguist too.
Yeah, I don't think I.
You don't think?
No, if that,
Then this,
if that. Oh, I guess. I don't know. It just
comma,
doesn't sound like speaking.
then the limit as x goes to a of this equals the limit as x goes to a of this, if the latter limit exists. It's like a clause, right? It's just a clause. Johnny, tell us when you're ready.
Okay.
Johnny gets to decide. The next thing I am going to do is ask us to use this rule, though, on the last example, which was like x squared minus 4 over x minus 2, right?
Johnny, wait 20 minutes.
I'll wait 20 minutes. Class is over.
Where's the elimination? The other thing you could do, Johnny, is like look at the proof, absorb it, and then recreate it.
I'm like on the last thing, so it's too late.
The idea of the proof, I hope, is in everyone's head right now. I think you could, many of us, even though we didn't write it down, maybe could reproduce it just right now if we needed to. All right, let's do it now. The thing I said, and that's to return to this example. Go ahead and try this now. What we're said to be able to do, according to the thing we just proved, is we already know. Yeah, I know we know the answer, but it says since this is indeterminate, first of all, verify that that's true. If x is 2, that we have the indeterminate form. Check. Next, verify that. Next, actually take the derivative of the top and bottom. If we consider the top f and the bottom g, then what are we really taking the limit of now? Yeah, 2x over 1, right? So apparently, so first of all, let's just realize that we really do have this indeterminate form. Check the box. All right, and then by L'Hopital's, we have that this limit will be equal to this limit, which is, of course, not really any work at all to do, right? So, in fact, actually, you might like that better than the trick from Unit 2, right? Maybe you think that's faster. At this point, maybe we haven't convinced you that L'Hopital's is like a powerful piece of machinery, but before you leave today, of course you will be convinced of that. Even after doing this next example, for example, which I think we maybe could have given you in Unit 2, but I don't think we probably would have on like a test or quiz or something. This would take a lot of algebraic trickery to use like kind of old school techniques on this. I think we'd like to try using L'Hopital's. Before we use L'Hopital's though, can you even just verify that it even is indeterminate? Plug in 0 and tell me. On the bottom we get 0. On the top we get 0 too.
Is that 1 minus the fraction?
Yeah, sorry.
Okay, it looks like.
And that's a period, Amy. Okay. Because it's a sentence. Okay.
Okay, but the comma one.
I know the comma looked like. That's why I know.
That was cool.
Now I'm just.
And when I retook it, like that was like the reason I got a fucking.
Because it looks like a prime or
Wow,
something.
Mr. Chase. And then I had to like retake it, and
See?
like, I had to figure out myself. I couldn't figure out what I did wrong.
So are we right that this is indeterminate? Is it quick to see that if you plug 0, you get 0? This is again 0 over 0. So this is one of those indeterminate forms, and L'Hopital's applies. So let's take derivatives on top and bottom and replace the top and bottom with the requisite derivatives. Well, that's 2x downstairs. Upstairs we've got 1/2, 1 plus x to the negative 1/2 times 1, I guess, by the chain rule. The minus 1 goes away, and we also have a minus 1/2. How'd we do? Plug in 0. It's indeterminate, but let's just take stock of where we are in life. Isn't the thing you want right now in your life, forget the original problem, isn't this the thing you want? The limit of?
Are you doing this again?
I think we should just do it again.
Yes.
If it's still indeterminate, which someone has told me that it is.
Oh, you can just keep going.
I mean, this is a new problem. It's the same. It still satisfies F and G, satisfy the the hypothesis of L'Hopital's. So I think we can just do it again. So let's do it again. Here we go. Negative 1/4, 1 plus x to the negative 3/2 minus 0 all over 2. Well, now are we ready finally?
Yes.
Okay. I think we can do it. It's not indeterminate anymore. Plugging in 0 is not a big deal. Even though we've got this messy power, that just comes out to be 1 up there. So we get negative 1/4 divided by 2, which is negative 1/8. Feel free to, by the way, to adjust. Feel free to try to just verify that you get negative 0.125 on your. You could actually plug in 0.01 to this expression on your calculator or something, and just kind of get a reality check that this is actually making sense. Maybe. I think it's important that we underscore that this is allowed, provided that we still have an indeterminate form, right? We can keep doing this, provided that we still keep having an indeterminate form. Again, first, verify that it is even indeterminate at all. Keep in mind that if it's like, this one isn't this way, but keep in mind that if it comes out to be like 7 over 0 or something, that's not indeterminate. What is that? Yeah, it's just undefined or infinity or negative infinity, right? Indeterminate right now, the only indeterminate form we've discussed today is 0 over 0, right? There are others, but 7 over 0 is not one of them. Okay. I guess we're maybe out. You want to go get some more tonight? Or I do have some more, and it's actually locked up behind it. How are you doing out there? So it is 0 over 0 here, right? So we get sine x over 2x. It's our favorite derivative. Oh, plus 1. Plus 1. Okay, and then we take the derivative again, right? Oh, it's not indeterminate anymore?
It's not.
Oh, okay, all right, good. So we're ready to plug in 0 now, can we? 0 over, 0 over 1. Is that okay?
So it has to be 0 over 0.
0 over 0 is indeterminate. 0 over 1 is not indeterminate. 1 over 0 is indeterminate. That's just either infinity or negative infinity. Right? So again, I just want to illustrate if this would be bad, okay? If you were in the position you were having so much fun taking derivatives and you got carried away, you'd be like, oh, okay, well this is cosine x over 2, so the answer is a half. Notice that would be incorrect and bad, yes. Okay, don't be this person, okay? Okay. Again, let me underscore what we said again, that this only applies if it's still indeterminate. Okay? 0 is the answer. Alright. Thank you, guys. I know you're excited to hear about some other indeterminate forms. So here are some other indeterminate forms, which you've already actually encountered some of this in Unit 2. For example, if you have an expression of the form something that's going to infinity minus something that's going to infinity, you kind of might have that question, like which one wins, right? We're subtracting. Infinity plus infinity is not indeterminate, right? Because like both of them are pushing you to infinity. But if one thing is going to infinity, you're subtracting something else that's headed toward infinity. The question is like which one wins, right? Or do they tie somehow? So that's indeterminate. We're not sure who wins in that battle. Why is infinity times 0 indeterminate?
Because infinity times 0 is 0. Because infinity's not a value, so you can't.
Yeah, I know. Let's keep in mind that these are two functions, by the way. F going to infinity and g going to 0, right? So the question is, if you have something that's super, super, super small, 0.00001, and then something that's really, really big, again, do you see the competition? Which one wins? Normally, if this thing is headed toward like a million, billion, trillion, and you're multiplying it by something, if I didn't say anything more than that, you'd be like, oh, well, then the whole thing is getting big. But if I didn't also, what if I told you also, though, that the other thing was drawing that thing down? Well, then which one wins in the end? The answer is we don't know unless we actually run some calculations and some analysis again.
So where would we get an answer that was infinity to the 0 power or infinity times 0? Because in these past ones we've been getting like single answers.
Yeah. So we'll have to again we'll have some expression like if you have here you might have root x times 1 over x or something, right? Doesn't root x go to infinity as x goes large? Yeah. And 1 over x as x goes to infinity here goes to 0 or something like that. So all of these will be fleshed out with some examples in a minute, of course. Yeah, Jackson and then Jack.
Wait, so if it's multiplication, can you just turn it into division?
And that's what this next thing says, is like in the end what we want to do is we want to turn all these back into the form we started with today. And so that's what we're going to do. Like for example, this form will be able to be turned into 0 over 0 with just a little bit of algebraic trickery. And then we'll just do as we did before once we do the algebra on the front of the problem. Yeah, Jack.
Okay, I'm like a little confused. Like, why isn't it just 0 with the second one?
Yeah, so again, let's keep in mind, I realize that's confusing because like 0 times any large number would still be 0. But again, these are not two functions that equal infinity and 0. We're talking about, these are indeterminate forms. We're not asking whether infinity times 0 is something. We're asking what happens when you have, what do you get here as x tends toward a, where a could be infinity too. And we're wondering, what does that equal, given that this is infinity, and this is 0. So when we're talking about the indeterminate form infinity times 0, this is really the fleshed out discussion of what we mean, right? We're saying not what is infinity times 0, but what happens if you have a function headed toward infinity and a function headed toward 0, right? Does that make sense? Why there's a difference here? All right, so let's try one, in fact, of which form? I don't know. You should decide which one this is. Yeah.
For 1 to any power, is it still 1?
Again, yeah, so this is a little tricky.
Same answer as that one?
Yeah, I'm going to do the same thing over here.
Right.
Again, we don't have, you're right, 1 to any power is 1. True. But what about something that's getting increasing, like say this is 1.0001, and I don't tell you what the exponent is yet. What do you imagine that is very close to still? If I said I have 1.000001 to a power, you would guess that I still have something that's pretty close to, not 0, 1.0001 to a power.
Okay.
Be very close to 1, right? But what if I told you the power was like a Google, right? Then you'd be like, oh, actually, I take it back. It's really big. You know what I mean? Like, so again, it's about those two things heading to those two values, right? Yeah. So I don't. These are kind of shortcut ways of writing down the real discussion I wrote over there on the board. Yeah.
Wouldn't that be anything to the power of infinity? Like, because it is 2 to the power of infinity.
Well, if we have something that's, I don't have any real question that if I guess I'm saying that if you have, if you told me that I have some function that's headed toward 1, like say x over x plus 1 to the 17th, right? Even though that's a big power, what does this head toward? What's the limit here? As x goes to infinity. As x tends toward infinity, this heads toward 1. Do you agree?
Yes.
Yeah, so I guess this is what I'm saying, is if you have a function here that's headed toward 1, regardless of what this exponent is, this thing heads toward 1, right? Now I haven't even put a function of x in here yet. So I'm just saying that definitely heads toward 1 if this base tends toward 1. But now I guess here's the big question is, what would happen if I put that now? Ooh. Well, now I don't know. Do you? Because this heads toward 1, so my first guess, like I said a second ago, would be 1. Because this heads toward 1. Oh, but wait. That makes this thing get really big. Now notice that there's just no debate at all. What about this one? What does that head toward? No.
Why?
Oh, yeah, 200%, yeah.
Yeah, it's going to be something enormous, right? So now it's not headed toward 1. It's headed toward something big. And if I ask you this, what is there any debate about what this goes to? What does this go to? This just goes to infinity, right? This makes things big. This makes things even bigger. There's no competition here, right? Yeah. No. These are the kinds of discussions that will keep you up at night. This is good. All right. Yeah. I mean, and if you some of these we haven't discussed yet. You should really have a discussion with yourself about this one. What about this one? Right? Come up with some examples that really boggle your mind for each of these. All right. All right. Which indeterminate form are we looking at, friends? Here. There's only maybe one that it could be up there. Yeah, it's infinity times 0, right? X certainly, as x goes to infinity, x goes to infinity. And the sign of 1 over x goes to 0? Oh yeah, because 1 over infinity will be 0, sine of 0 is 0. Okay, so I think I'm good. All right, so we're in this situation. We're in the infinity times 0 indeterminate form situation. Check. And then obeying this little tidbit here, let's now manipulate this using, someone suggested this. Is this what we're going to do? And the answer is yes. We're just going to use previous technology. Let's get it into a fractional form of an indeterminate form. And really, either one of these will be fine. If you have infinity over infinity or 0 over 0. We can get it into 0 over 0 form, though. How would we do that? Again, this is pure, just algebraic trickery. Can you rewrite this? Yeah, sine 1 over x
Over 1 over x.
over 1 over x. Oh, look at that. We've just transformed it into the form that we used before. So maybe this isn't ready to be directly plugged into our L'Hopital's rule from an earlier slide. But this is. It's now in the form, the indeterminate form, 0 over 0. So I hope you can see that, in fact, this is our only technique for all of these, is going to be to get it somehow into this form. That's going to be like the whole game. And once we do, we just do what we did before. It's indeterminate, so we'll take derivatives. Chain rule. Yeah.
What if you were asked as it goes to 0 and then 1 over x would be 1 over 0, that would be 0 over 0, that'd be...
For this particular example, you mean? You'd have 0 times 1 over sine of 1 over x near 0 is undefined. It's like asking what is sine x? What's happening to sine x as you go out to infinity? So that wouldn't be indeterminate. It would just be undefined in that case. Yeah. I think we can just use algebra here to cancel. So we have the limit as yeah, I guess we should say doesn't exist.
Is there a difference between...
Undefined, I guess we usually reserve for a function at a value, right? Whether it's defined there or not, or derivative. Yeah, so what do we get here? The cosine of 1 over infinity. What is the cosine of 0?
My grade is indeterminate.
Yeah. John.
What's the exact definition of indeterminate?
So,
Those numbers, memorize those numbers.
yeah, just memorize all those numbers. You put me on the spot here, Johnny. Something we're confused about? No, that's not good. Let's see. Could we just say something that could be transformed in the form 0 over 0? I do think you have to go through the work of proving, if you really wanted to trust my claim that all these are indeterminate without just being like, oh, it's obvious. You would actually have to prove that all forms of these types can be algebraically manipulated into this form. That's what I think you have to show. Right, which I don't think we could do.
You don't think I can do it?
No, I think we could do, I'd say. Yeah. Because this is not an accident. The thing we just did here always happens. Right? If you have this form, you'll always be able to do what we just did here. You can turn this into by putting whatever it was that goes to infinity on the bottom. All right, let's look at which form is this now. Which form is this?
Infinity minus infinity.
Yeah, infinity minus infinity, right? ln, this is a little bit, this one's maybe more obvious over here, that near, for 1 over x minus 1, which is just 1 over x shifted to the right by 1, that we have a vertical asymptote there, that is infinity. Is this one infinity too? Is that cool? What's ln 1? Or I guess I should say, what's ln of 1.0001 or something? It's something very, very close to 0 and positive, so we'll get a positive infinity here. So this really is indeterminate in this form. How do we get it into a fractional form when we have this situation? Well, we just combine fractions, right? Find a common denominator and go for it. So we have x minus 1 minus ln x over the common denominator. Is it indeterminate now? If so, which form is it in?
Something.
ln 1 is 0. Yeah, I think we now have it in this form, 0 over 0.
No.
Taking the derivative here is not super fun though. In the bottom we have to use the product rule, but everything will be okay. We'll use L'Hopital's now on the top, and the bottom we'll take derivatives. Limit. Come again? No, not really. So there's on the top. On the bottom, what do we have? 1 over x times x minus 1 plus ln x. Right? Oh, well, there you go. All right, more on L'Hopital tomorrow. I think we might have to do it again. Yeah, it's still 0 to 0. All right, more tomorrow. Make sure you do homework for L'Hopital. You need to finish Unit 4 practice. I'll let you do that too. Bye.